Good morning. So we pick up from the last class. Today is 28th of January. So this is a class number 5. We continue from the number 4 last time. So just a quick view. We try to construct the limit states for the member under tension in the last class, starting from the member without the both holes, and we assume that there is no shear lag problem for that given case A. So we have no reduction of the area. So we have A gross for all limit states. A net is not coming in because there is no such reduction. And then we move over to case B, C, D. So we started with the construction of the stress-strain model for this steel, where you know that the tension coupon is of the size 8 inch in length and 2 inches in width and 0.5 in thickness. So it's a flat bar tension coupon, and then you construct stress-strain relationship accordingly, and this stress-strain relationship is used for the following calculation. So case A was done already. One thing I emphasized you last time about the failure of the member under tension, the design approach allows, we consider two different kinds of failure mode. The first one is the fracture. So fracture will control the failure at the reduced or the A net section, whereas the gross section, A gross, controls just the yielding failure. Yielding does not lead to catastrophic failure. It does not lead to collapse, but it leads to the serviceability problem. So excessive deformation is expected from the yielding, and that's going to cause you the problem in that view. Whereas the fracture is going to let your structure, it's going to make it fall down. So the strength reduction factor, or something that gives you the factor of safety, is lower. So the 0.75 is a strength reduction factor that controls the fracture, whereas the yielding is controlled by 0.9 because it is the ductile kind of failure. Alright, so we will get through all these failure modes and limit states. So here, come back here, this is the case B. Before we start case B, we check the ratio of the gross area to the net area, and we check if this is less than the ultimate to the yield strength or not, and we found that the ratio is much lower. And we can conclude that the fracture over the A net comes after the yielding of A gross. So we will have these many limit states. So yield net, yield strain hardening net, yield gross, right? Because from this conclusion we're gonna have the yielding in the A gross, hardening A gross, and then ultimate of the net. Okay. So the forces correspond to all these limit states were calculated last time, but we still have the delta to calculate, right? And this is the picky part, it is the laborious part, so we will continue over here this time. I think it is easier to just copy this down, the whole thing, and we will have plenty of space to play. Okay, so the delta is brought down to you here. and then I don't need to squeeze out this thing. Okay, so the 1.6 centimeters just represents the bolt holes, the length, total length of the bolt hole, because you have M8. M8 means 0.8 centimeters and 0.8 centimeters on both sides. So the area that is reduced by bolt holes has the length of total length of 0.8. But let me ask you one thing. When the fracture occurs, do you think that it's gonna frac on both sides simultaneously? No. The constant cross-section frac only over just one given cross-section. You never see the tension cube on specimen get necking over two areas. The weakest link always go to the fracture, to the necking. So at this stage, we will use both point A and point A because this is a yielding. But at the fracture, there will only be just one bolt hole, either this one or this one, that will suffer from the fracture. So we will make the calculation according to that fact. Right. So 0.01 is the yield strain, and then over this area is the gross area, the other part that do not have the bolt holes, multiplied by, this is the ratio between the this is the yield strain multiplied by the stress ratio. So this to this is a force is a stress ratio between the other area or the stress on the A gross compared to stress on the A net. Alright, so we can use that interpolation. It's just a linear interpolation because you are still on the same straight line. Now we hit the calculator for the figure 1.6 times 0.001 plus 300 minus 1.6, and then multiply by 0.001 multiplied by 36.8 divided by 40, turns out to be 0.276. Actually, don't need to keep up to that. 0.28, good enough. Next, strain hardening. For strain hardening, nothing changed on the back, only just this thing change. Right, just the strain. This is a U. For this side, it doesn't change. Force is not changing. So the elastic deformation in the A cross will not change. Right? You just have the larger deformation in the holes, both holes area. So as simple as just delete this. Okay, 0.29. The figure is so small because this bolt hole is just very short, 1.6 centimeters compared to the entire length of the member, which is about 3 meters. So the part that governs the deformation seems to be the A cross. Now we come to the next step. The next step is the yielding of the A cross. So the part over here on the back is easy to calculate. 300 minus 1.6, then multiply by 0.001 as the A cross yield. But what happened to the A net? At the yielding of A cross, you know the force, right? Yielding of A cross force is equal to 1000 kilonewton. That is going to cause how much on the A net? So you take the 1000 for the stress, divide by 36.8 centimeters square, and then you just convert it to megapascal. 1000 divided by 36.8, you end up with 272. Oh, let's put it precisely, 271.7 MPa. Force has to be the same, but stress will be different. 271, okay, let's come back and take a look at this. 271 is going to be somewhere around here. The thing is that you just need to figure out the corresponding strain to this 271. Right? So you take this difference from 250, and then you do the interpolation of this line. This is a triangle. So the question mark minus 0.01 divide by 271 over 250 is going to be equal to 0.1 minus 0.01 divided by 400 minus 250. Okay, let me clean up this first and be writing that down over there. So I will giving you model okay, this is 250 MPa, and the next line is 271 MPa. Oops. Alright, then the interpolation will be carried out. So this you want to know this question mark minus 0.01. 0.01 is here. 0.1 is here. This is 400 MPa. No, I just need this. Okay. So let me write this down carefully. Stress let me just rearrange things around a little bit so it is possible for you to understand. Just take this down this way and okay. So 271 minus 250 it is 21.7. So we do the interpolation to find the question mark. I think I'm gonna make the boundary line like this. Okay. Okay, so 21. Question mark minus 0.01 divided by 21.7 is equal to 0.1 minus 0.01 divided by 400 minus 250. Make it easy for you to understand in the future. I expand it like to 71.7 minus 250. Okay. And that is going to make the question mark. is equal to 0.09 multiplied by 21.7 divided by 150, and that is 0.013, whatever. So you get that question mark. It is just about 0.003 beyond the strain hardening. So you come back here. 1.6 centimeters multiplied by 0.013. You got what? Different? From this, I didn't add up by 0.01, right? So it is supposed to be 23. Thank you. Thank you. 1.6 multiplied by 0.023 plus 298.4 times 0.001. .34 centimeters. And strain hardening of the A cross. Next step, it does not change the force in the A net, so the A net is still there, whereas the A cross is subjected to the new strain value, which is this one, which is equals to, let's just take out 1 0, and then that turns out to be 3.02 centimeters. And then we move to the next step. The next step, your A cross will be in the strain hardening, whereas your A net is experiencing the maximum, the ultimate strain. So 1.6 centimeters multiplied by 0.1. That's the ultimate, plus 300 minus 1.6 multiplied by your new strain in the A cross. So I'll be taking this to the next page. It is what stress in A cross at the ultimate strain of A net. So let's take a look. At the ultimate, it is 1544 kilonewtons. 1544 1544 divided by 40 square centimeters, and that's gonna make divided by 40. 38.6 386 386 MPa, so the curve will be .386. So this guy is there. Okay, just like this. .386. So we gonna find the question mark. 0.09 multiplied by 386 minus 250 divided by 150, and then plus 0.01. That makes 0.0916. And then we take this 0.0916 back here. .6 multiplied by 0.1 plus 398.4 multiplied by 0.0916. That makes it 36.65 centimeters. Now we come down to the fracture of A net. So as I remind you that the fractures, it will not break simultaneously for the two holes. So one hole experiences the maximum it's a strain at the ultimate level, whereas another hole 0.8 centimeters is experiencing the strain, which is the fracture strain. Epsilon y, okay. This is strain hardening. And this is equal to 0.8 multiplied by 0.1 blah 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 plus 0.8 multiplied by 0.5. That makes 36 0.97 centimeters. So, do we have a plot somewhere? Okay, we're gonna get the case B. So let's review. We have 920 in the market, 1000 and 1544. 920, 1000 and 1544. 920. I'm gonna put this red line. 920. So let's see. 1, 2, 3, 4, 5. This is 800. This is 900. 900. We have like this increments. So 2.5 increment associated with 100. Then one increment is 0.4. Half increment is 20. Okay, here. Okay, 920 is here. So I draw this line. This is 920. We have 1000. It's gonna be in here as well. And then we have 1544, right? So 1000, 200, 400. 1214, 15, 1544, right? So 15 is here, 1520 is here, 1540 is here. Okay, so the line gonna be difficult to see. This way. Okay, okay. You can see that the force level drops from the case A. The ultimate one is just coming up to that far. Now let's mark down the deformation values. So start with 0.28, 29, 0.3. So let's say about 0.3. Okay, and then 3. And then 36, 28, 29.3. Let's see how. Okay. If 5 is here, then here is 4, here is 3, here is 2, here is 1, right? And then this little increment, 0.2, 0.4, 0.6, 0.8, 1. Okay, so this is 0.3 is between there. Hard to see, yeah, 0.3. Anyway, it will be around this zone. Okay, 0.3. And then we have the 3 centimeters, which is here, 3 centimeters. And then 36, right? 3.02, 36.6 and 36.9. And that doesn't make a big difference. 36, seriously? 36. Previously for case A, what was the maximum? 33. Oh, because necking occur over a larger area for case A. No. We miss. No, we don't. Why is this case? How does it undergo larger deformation than 33? 0.1 multiplied by that, and then 0.5 multiplied by the larger fraction. Is there anything wrong? 0.1. Okay, let's say 0.1 multiplied by. Just check first. I'm not sure. So this is about 0.1, and then 0.8 multiplied by 0.5. This is strange to me. Okay, let's say less than. Hit the calculator again. 0.8 multiplied by 0.1. That is 0.08, right? And then add up with 300 minus, which is 298.4 multiplied by 0.0916, then plus 0.8 multiplied by 0.5, 27, right? At least we know that something went wrong. 27.81. How about the top one? 1.6 times 0.1 plus 298.4 times 0.0916. 27.49. Okie dokie. 27.49. 25 now. 26, 27, 28, 29. This is 27. We have 27 point something and something. Okay, fine. Alright, this is 27. So we're gonna draw the line from here. 27, I come back, check what is it, 27.5 and 27.8, 27.5 turns out to be a little bit to here, right, 27.5 and 27 point, wrong, copy first. 27.8, which is around here. Okay, beautiful. Now we'll write this line down in purple. So we have the yielding at the 920. Yielding of the A net, strain hardening of the A net is just a little bit. The strain is so small, and then later on it jumps up. I will borrow the ruler again. So let me just make sure. Yielding and strain hardening seems to be just 1 point, and then yielding of the A gross is 0.3, which is 1000. Okay. and then A cross just go to 3, yielding of A cross just go to 3. Okay. So, well. And this area, you have just a bit of this, right? And then you go up a bit to this line. Sorry, I keep pretty much. Okay. Now, from this 1000 here, you will be going to the $1,000, okay, and then go to 3, right? Okay, go to 3, okay, 1000 to 3, which is to this point. Oop, okay. And then from 3, it's just gonna go all the way to there. So I mark it there to there, alright? And then just there, that's it. And then I clean up the lines. Delete. Okay. Alright, okay. Good. This is case B. A little too small. Case B. Pretty much like case A, but it just cannot make it to that far like case A. Okay, we'll continue. So we come down to case C. What is this? So for case C, we'll come down here. We check of this. Run off space. Okay, come back. Redo it again, just copy this. Okay, and we still have space then. 40 minus what? Now it is M25. M25, the cross section you had 25 add up to 50 millimeters or 5 centimeters. 5 centimeters multiplied by the thickness of 2, then you get 10 square centimeters. 10 square centimeters will be gone from 40. Alright, 10 out of 40. So 4 divided by 3, still you get 1.33. Less than 1.6, then the limits that we put over here still works. So start with the yielding of the A net. You get the 30 square centimeters multiplied by 250 MPa. That makes the 750 kilonewton. And it is the same here, which is equals to 750 kilonewton as well. Yielding of the A gross 40 1,000. That is equals to 1,000. Ultimate of the A net 30 square multiplied by 400. You can see that it drops to 112.00. 1200 kilonewton. Alright, and then we come to the next page. Deformation delta. I'm gonna take this thing, copy from here, put it there. And this one here. Put it there. Right. So you don't have that privilege. I'm gonna make adjustment to the figures a bit. Later we will come back down here to adjust the number. Okie dokie. Nice. Okay. Oh, probably just copying this for further use, but I don't think. Paste it here, just in case if I need to use it. Alright. Done with force. Now come down to deformation. So start the yielding of a net. You have M25. There are two rows of M25. So that makes 50 millimeters. So 5 centimeters multiplied by the yielding, which is 0.001. Add up with 295 centimeters, which is subjected to the strain values to be determined 0.001 multiplied by 75 divided by 100. That 75 to 100 is the area ratio. Basically it is just 1 to 4, like 3 to 4. Which is equal to and then 295 times 0.001 times 0.75. That makes the 0.23 centimeters. And then strain hardening. So the whole thing gets copied down. Only just 1 0 is removed, and that makes 27. At the yielding of A gross, so this part is gonna be easy. 0.001. That's it. And how about the this point here? Yielding of A gross is 1000. This is 30 square centimeters, so you get the 333.3. Coronavirus. Yeah. Don't worry. Be proud, you get coronavirus from me. It is much better than get it from others. You go talk to others like, hey, I got corona from Dr. Panchet. Yeah. It's not bad. Yeah. Divide by 150, multiply by 333 minus 250. That is plus 0.01. Oops. Okay. 0.09. Divide by 150, multiply by something like that. Oh yeah, 0.01. Okay. This is equal 0.0498, right? If you get the same number? No? Yes or no? 598. I didn't add 598. Yeah. So, what? 0.0598. Okay. Yeah. 9899. Fine. It doesn't change the third, fourth digits. 0.0498. Okay. Let's make it 0.05. 5 times 0.05 plus 295 times okay, 0.545. Oh, then it turns to be 6. Okay. Thanks. 595. Strain-hardening of a gross. .25. And ultimate strength of a net 5 centimeters times 0.1 plus 295 centimeters multiplied by. Okay, so ultimate strength, what is that load? 1200. 1200, we bring it in here. 1200, that makes a 300 MPa. 300 MPa. A cute number. But 0.09 multiplied by 50 divided by 150, and that add up with 0.01, that is 0.04. 0.04. Yeah. 0.04 in here. 5 times 0.1 plus 295 times 0.04. 12.3 centimeters. And finally, you have 2.5 and plus 2.5 centimeters multiplied by 0.5, and that is equal to 14.8. I'll be taking all these guys to tour. Oops, no, undo. Just copy. Yeah, put it on this page, easy to see. And we have what, 750, 1000 and 1200. Okay, so I don't need to go far. What will be the color for this one? The green. Yeah, the green is good. Right, so what we will start marking down the thing. 0.23, 0.27. Yeah, it's gonna be somewhere around here. We need the 750, right? 750, this is what? 2, 4, 6, 8. So 6. Here is a 7. 750 is here. Okay. 1000 and 1200 is here. So let me put the line. Shoop. There. Okay. And 0.23, 0.27. This is like to the left of the given for the purple line. And 0.6, 4, 3, 2, 1. Okay. 0.2, 0.4, 0.6 is here. 0.6 is there. Then okay. 0.6 is like here. Okay. Good. Then 0.2 will be somewhere there, and then drip, and then jump up to 0.6, 0.23, 0.27, and then 0.6, 3.25, 1, 2, 3, 3.25. This is 3.2. 3.4, 3.6, 3.8, 3.25 will be just a little bit, just a little left of that line. It's just a little to the left of this line. Yep. We get 3.25, 12.3, 12.3. 14, 13, 12, 11, 12.2, 12.3 is just in between. 12.3 is just in between. Yes. And but 14.8, 14.8 is this line. Okay, there it is. Okay, let's draw. Let's draw the lines. Which one? Which one? 30? 13.3. Okay, I did it again. This one? Oh, 13 point. Yeah, it was supposed to be 5. Okay, it was supposed to. Okay, let me. 13.3. Okay, yeah. Thank you. .3. 13.3, then move this 13.2.3. and then it just chip a little bit like that, and then to 1000, and then it go to 3 point something. Can use this one now. And then just come from this to this point, and then from this point to this point. That's it. So this is case C. I think we will be able to make some sort of observation out of this one here. We will later plot the curve that is according to the requirement by AISC in the design. Because right now we are tracking the limit state. This is what actually is gonna happen, but it is not what the code tells you to obey. Not yet. It will be included in here. Alright, here, clean, and come back here. So, last case then. Case D. Case D, what might be a good color for it? The red one, we have not used the red. Case D. So let's go check. Case D, the hole is M30 and 3 of them are there. Are you serious? You could be more serious, 3 M30, M75, 20 minus 7.5, and then okay. 20 minus 7.5 and 20 divided by that. It is, if it is 2.5, then it is just right at 1.6, so everything is gonna happen at the same time. Okay, M30, this is okay. This is good, so it is not on the borderline. $40 minus then 18, right? $1.8, 1.82. Instead of after, it is before. Thus, limits that we used to have previously is going to change. Yielding of A net, of course, it happened strain hardening of a net, of course it happened, but the gross is not going to be inelastic at all. That makes our member behave like this. So yielding 40 minus 18, what is it? 22 square centimeters. Multiply by 250 MPa, and that is 550 kilonewton. Likewise, for strain hardening, it is 550 kilonewton. And then 22 square centimeters multiplied by 400 MPa. That is 880. You can see that the capacity at fracture is less than 1000, which is the A gross yielding. And here's the thing. So come here, limit states for the deformation. Yielding deformation, we have 2 multiplied by 30 millimeters, so 3 centimeters, multiplied by 0.001 plus 294 centimeters multiplied by 0.001 multiplied by 22 divided by 40, which is 6 times 0.001 plus 294 times 0.001 times 22 divided by 40, 0.17. Strain hardening, so remove 0.22, very small. And then ultimate this one out, this here. You just need to figure out strain in there. So stress in a net at the yielding over stress in a gross at the ultimate of a net. I'm gonna pick this one up. Hope it fits here. No. Okay, fine. Sorry. Put this one here first. Put this in here. Okay. This one change to what? 880. 880 divided by 40. Oh, it's not even yield. Oh, sorry. So. What is it? 880 divided by 40. It is okay. 22. You just need to put a bit more. So this is 22 multiplied by 400 divided by 40 to 50, right? Is that so? Okay, don't just make you confused more. 220 MPa. Okay. 220 MPa. So 22 divided by 25. Just that. Okay. Yeah. Makes sense now. Right. 2 times 3, 0.1, 294, and then this ratio and the stress ratio is 220 MPa. So basically this guy here is, we don't need this interpolation because it is not above the yielding. We have the interpolation done over this zone down here. So okay, so 220, right? Okay. So the question mark turns out to be 0.001 multiplied by 220 and 250, just that. So calculate this. 0.6 plus 294 times 0.001 times 22 divided by 25, 0.86. And this part here, so not 2, it is just there, and then another 3 centimeters multiplied by 0.5. So that means 3 times 0.6 plus 294 times 0.001 times 24, 2.06 centimeters Wow, 9:50 already. So bring them all there. $550 and $880, okay. So what I need, 0.17, 0.22. Okay, I need to cross the 550 first. $550. 2, 4, 6. Here it's a 5. 550 is here. And 880. This is 6. This is 8. 9 is just here, so 1 mark is 20. This is 880, and this is 550. Alright, 550 and 880. And 0.17, 0.22, 0.86, 206, 206 first, easiest. 206 is here. 0.86, where is 1? 0.86, it is close to 0.9. Okay, 0.86 going to be around there, and what 1 something, 0.1, 0.2, 0.1, 0.2 is going to be around there. Okay, so boop boop, and then okay, got it. And then it goes from this point to here, alright, and from this point to here. That's it. No more useful. No longer useful. Delete. Okay. Should be the last time. Case. Oops. Case D. Now, I'll copy this page. Copy. And now do I paste? Done. And boop. And add it here. Paste, copy, page. Okay. Done. Good. Okay, so I have a backup. Now talk about case A. Case A, you don't have the reduced area. You have full area for this case only. The only limit state is building that is used to yielding of the cross section. So no matter how high this one is, it is not used to control, because the yielding is going to be the mode of failure that control according to the AISC. So 1000 is the capacity, yielding capacity, then it is back down to 900 due to the strain reduction factor of 0.9. So there you go. I will draw this. Okay, move it a little bit. Okay, and write it down. This is the yielding. No ultimate. Okay. Next, for the case B, you have both yielding and the fracture. So let's see which case control. Yielding of case B, you can see that the purple line yield at the same point as the case A. So this solid line is gonna be share. First, I need to change this color to purple, right? Done. Likewise, for case C, it's still yield at the same point. Now we write the fracture control mode. So for case B, the figure is ultimate 1544. 1544 multiplied by 0.75, you get 1158. 1158. This is 12. This is 11. Okay. 11 to 12, 1120, 1140, 1160, 1180, and 12. Okay. So 1160 is here, which is about 1158. So case B. Which one? This one. Okay. So I specify that it is a fracture. Next, case C. Case C is 1200, right? Multiplied by 0.75, it is 900. Is the same. So I say that yielding of A, B, C, and fracture of case C. Basically, case C is the most cost-worthy in that view, because the phenomena is going to occur at the same time. But it will, if you consider the factor of safety. But in reality, the limit state, the real limit state is going to go just to here. You have 0.75 for fracture, so you are pretty much ensured that your member is going to go all the way to fracture. It will not frac before the yielding. You will have this zone for sure. Fracture of case B is here, fracture of case C if you want to write the fracture of case A, not necessary. And the case D, you do not have the gross member yielding, so you have only just the fracture. So 880 multiplied by 0.75, you get 660. 660 is 2, 4, 6, 8. So 6 to here, this is 700, 20, 40, 60. This is 660. Okay. Fracture of D, which is 0.75 multiplied by 880, 660 kilonewton. Yielding of ABC, which is 0.9 multiplied by 1,900 kilonewton. Fracture is from 0.75 multiplied by 1200 equals to 900 kilonewton as well. Fracture of B is equal to 0.75 times 1544, which was equal to 1158 kilonewton. Okay. So the difference is the ductility. Now, for case A, case B, case C, same capacity, then you have the ductility as the issue. So that depends on how much ductility you need from the design, right? That's the part that will concern you from structural analysis. You can run and see how ductile your member should be in order to be able to carry the load all the way to the ultimate level as you prescribe. Okay, so I'll be circulating this handout to you so that will be uploaded on the Google Drive. Okay, page 1 to page 1 to 8. Alright, so see you tomorrow.